We want to know, what is this transfer function doing at different frequencies? We'll take the magnitude of it to see if it amplifies it or if it reduces those frequencies. So it's the magnitude of e to the j omega plus j. What we're doing here is we're finding the transfer function e to the j omega by just substituting e to the j omega into z. And then we'll find the magnitude of e to the j omega minus j, divide that by e to the j omega plus 1/2, and multiply that by e to the j omega minus 1/2. Okay, so far it's just been a direct plug-in. Again, big picture, what we're trying to do is we're given some sort of transfer function. We can see it's got zeros at j and at minus j, and it's got some poles that are at 1/2 and minus 1/2. And we'd like to know, is this a high pass filter, low pass filter, or what? If we were to take MATLAB, we could create an omega function and let it go between 0 and pi and give it a bunch of things to calculate. And then we could actually calculate what our h is. From our left thing, it would be exponent of j times omega dot times exponent of, and we could continue on that. And then we do a dot divided by two things and dot times two things. And we'd have our whole h. Then we could plot our omega versus the absolute value of h. And that would tell us what the frequency response is, given this h of z. Is everyone with me so far? I just want to get a thumbs up, because it's easy to get lost in what we're doing if you don't see why we're doing it. What I'm going to do is tell you how you can do this by hand without MATLAB, just visually, which sounds impossible. But watch how it's done. There's a geometric interpretation of what this is. Magnitude, all that the magnitude means is it's the distance of a point from the origin. Let's take a look at this. This is the distance between, just like this means the distance between 3 on the number line and 2 on the number line. This means the distance between e to the j omega on the complex plane and j on the complex plane. So e to the j omega is just a point on this thing. Now here's, that dot was in the wrong place, but this might be omega equals pi over 4 radians per sample. This might be omega equals, what would that be? 3 pi over 4 radians per sample. Down here would be omega equals 0 radians per sample. So when we plot a frequency going into our system of omega, because this is e to the j omega, we're really plotting a point on this complex number line. This is this, or that, for different frequencies. So now let's just look at it for one particular frequency. I'm going to simplify this thing down and just write one frequency. I'm just going to use this frequency here. Omega equals pi over 4 radians per second. What this section right here represents is the distance between this point and the j. It's that length. And similarly, this one on the left represents the distance between this e to the j omega point and that 0 over here. And then in the denominator, we've got the distance between that pole and that pole. So what this system is doing at this particular frequency of pi over 4 radians per sample is equal to the product of the distances from the frequency to the numerators here, divided by the product of the distance from the frequency to the poles. It's pretty hard to see what's going on here, but what I'm telling you is that if you were to move this frequency low, can you see how it's very close to this pole? That means you've got one number that's really small in the denominator, which means it's really big, and that means that it passes low frequencies. Similarly, as you move it over on this side to the highest possible frequency of omega equals pi radians per sample, now this distance is going to be really small in the denominator. So no matter what all the other lines are doing, you're going to have a really big number, and it's going to pass high frequencies. And then in the middle, for omega here, this corresponds to omega equals pi over 2 radians per sample. Here, there's going to be 0 distance between your frequency that you're analyzing and this 0. So at omega pi over 2, we're going to get a 0 in the numerator, and that means it's going to kill our response. So just by looking at it, I would expect this thing to have a magnitude in the frequency domain of things that pass low frequencies, stop intermediate frequencies, and then pass high frequencies. And then you can see from the symmetry how as you rotate this around and around, this will have the negative, the proper symmetry. Thumbs up. I created a app. It shows that with these zeros right here, now we can actually see what happens is we increase our omega from 0, and as it gets higher and higher frequencies, this is an intermediate frequency, and this is the highest possible frequency we can have, and then after that, it just mirror images it on the other side. And you can see that at these low frequencies, your output response is equal to the product of these guys, which doesn't really change a whole lot as we move around here, divided by the product of these guys, and this gets really small, and so that's why we've got this peak over here. And then as we increase our frequency, to this pi over 2 radians per second, it falls right on top of a 0. And as we increase our frequency still higher, now this line from this pole to the frequency is getting small, the denominator. So that's why we see an increase. And so therefore we've got this DTFT down here, which shows that it passes, blocks. So you could call it a band stop filter right around for intermediate frequencies. Joe, I haven't called on you yet. How would this frequency domain thing change as I move this pole closer and closer to the unit circle?
I'm guessing the line would become steeper. So it becomes steeper. I don't know how else to describe it.
As I move this pole closer and closer, we're going to find for low frequencies that this distance gets smaller and smaller. So the denominator gets smaller and smaller. So we're boosting up these low frequencies. Joe, what would we do to change it so that it would boost the high frequencies more?
Adjusting the 0 that's on the high frequency side, so towards pi.
That's it, except it's not a 0. This is a pole.
Or a pole. Yes.
And sure enough, as we move it closer and closer, we get a boost here. And as we pull this 0 away, we get a reduction in how much intermediate frequencies we move. So now you can quickly see that if you wanted to get just a really rough, say, low-pass filter, can you see how putting a bunch of poles on the left half plane will definitely pass low frequencies really well. And then we can kill those high frequencies by just putting a bunch of zeros on the high side. Let me stop showing all those lines just to make it a little bit clearer. But now you can see we've got a really good low pass filter. This is the low pass region. This line is at omega equals pi. This is the highest frequency, and we've done it. And we can see how if we wanted to destroy maybe this frequency in here, we could put a 0 right on that frequency, and we just kill that one particular frequency and still otherwise maintain what the system is doing. So here's one for you. I'm not going to show you the frequency response anymore. I'm going to show you the time response. I'm going to ask you, what does this filter do just by inspection? What does this filter do in the frequency domain? Is it low pass, high pass, band stop? What kind of frequencies does it pass or stop? John? You can't tell from the time domain. I'm about to show you, but I want you to give your best guess.
High frequencies.
Well, let's see. At high frequencies, this is high frequencies. So is the distance long? Do you have a big numerator or a big denominator, or a small numerator or a small denominator? The thing that most influences high frequencies are the poles and zeros closest to it. What are the poles and zeros closest to it? Are they going to be poles or zeros? John?
They're going to be zeros.
They're going to be zeros. So it's going to be heavily influenced by the short distance to this 0. So the 0 will influence it at high frequencies. Tell me, will that make the thing big or small?
Would it make it smaller?
It'll make it smaller. You'll have a short distance, a small thing up here. And the same reasoning is true for these low frequencies. So what you'll get is a bandpass filter. And we can see that in the frequency domain. And in fact, you can get rid of these zeros and it's still roughly a bandpass. There is one thing I did want to mention just before you go, and that is when you take a look at the time domain, I want you to see that no matter how many zeros, no matter how many poles we have, and no matter where they're placed, zeros can be anywhere. They can be left half plane, right half plane. That thing about things being unstable for the right half plane, that's only true for continuous time. When we're working with Z transforms, it's a different rule. Like continuous times, zeros can be outside the unit circle, inside the unit circle, left or right half plane. And we always see our time thing being stable. The moment we move any poles, though, outside the unit circle, the further outside, the more unstable the system goes. So the moment the pole is outside the unit circle, our system is unstable.